Okay, in the video where we calculated the average surface temperature on Mercury, we derived the equation. The temperature was equal to roughly 279. I actually calculated 280, but I'm not going to get into that. 1 minus the albedo to the 1/4 power times the distance in astronomical units to the negative 1/2. And this is from the slides, PowerPoint slides from week 5 Wednesday, slide number 21 is where this question is coming from. Okay, and we're looking for solid water ice has an albedo of 0.35. What is the minimum distance from the sun at which an ice ball would remain frozen? So if we have our sun, and as you get further and further away from the sun, obviously things get cooler and cooler and cooler. They fall off at 1 over r squared. We have our little planets. Let's say Earth and Mercury. We know Earth is at 1 astronomical unit. Mars is at about 1.5 astronomical units. And we know somewhere along this path that if you have let's say you have a piece of ice. Let's make a big chunk of ice here. Okay, that's quite a bit. Maybe a little bit exaggerated, but you have a chunk of ice. Is it going to be liquid at this point? Is it going to be liquid at this point? Or is it going to be ice? What is the minimum distance where a big chunk of ice can travel towards the sun and still remain ice? So we're trying to find that distance in astronomical units. We'll just put a question mark. Is it here? Is it there? We don't know. Where is that minimum distance? Well, it says that assume that the ice ball is rapidly rotating to maintain a uniform temperature across its surface, so it doesn't get warmer on one side and colder on the other, allowing it to sublime. That is the big hint here. The sublimation temperature for ice in a vacuum. So if we're out here in space, we're not going to be dealing with ice melting at 0 degrees. This is extremely low pressures out here, and it will sublime at those pressures when it reaches 200 Kelvin. Okay, so that's a setup. Solving this equation for the distance, this is the same thing as temperature equaling 279, 1 minus albedo to the 1/4 over. Take away our negative sign and move it down here, distance to the 1/2. Okay, now we can multiply by square root of d and divide by the temperature, basically just switching these out. So our distance squared is going to be equal to 279, 1 minus albedo to the 1/4 power over our temperature. And what temperature is this? This is the sublimation temperature. That was 200 Kelvin. Okay, in order to get this into units of D, we multiply by 2, or raise each side by 2. That gives us our distance is equal to 279, 1 minus the albedo over the temperature squared. So this is going to give us our distance at which ice can remain remain ice instead of liquid water in astronomical units. Okay, this works out to be, let's plug in our numbers now, 279 times 1 minus the albedo was 0.35, so So this is going to be 0.65 raised to the, almost forgot something, raised to the 1/4 power, so the 4th root over our temperature. Our sublimation temperature was 200 Kelvin, and all of that squared. And upon all of the calculations, we're going to get the distance at which ice moving in towards the sun, in which it remains frozen, is going to be equal to 1.57 astronomical units. And this is, if we were to look at our little picture up here, one just over the orbit, just a little bit past the orbit of, this is Mars. So if you have a piece of ice, a little ice ball rotating, and it's moving closer and closer and closer, right before it gets to Mars, it should liquefy. And that is that problem.